things mostly don't change actually. Okay. So I'll be talking about this recent work with Shubham, students at IISc. It's on these transport coefficients, which we'll see constrained by anomaly. So let me begin with the introduction and motivation to the question. And I will. This is a system which I will discuss most of the talk, and maybe towards the end I will move on to 4 and 6 dimensions. But this is very simple to get all our ideas focused on. So basically, we look at charge relativistic fluids in 1 + 1 dimension, and their constitutive relation to the leading order is given by this expression. You see there's no derivatives in the velocity, and this is the leading order. This is the perfect fluid part. And here are the coefficients which is of interest here. In the stock, basically, here there is a coefficient lambda 2, and in this current there is a coefficient theta 2. And this also comes with an excellent tensor. The excellent tensor in 2 dimensions, so we would sort of think it is parity odd, and this is the transport coefficients we are interested in computing. And the others are the usual variables, energy, pressure. We use the same epsilon symbol for both, but I think it is clear. And these two, and we have written it in a little different frame than people who are familiar with in hydrodynamics. This is something called anomaly frame, and it's easy to evaluate them directly. I mean, it doesn't satisfy, for instance, the Landau frame condition, u mu q mu is equal to 0. So these are the coefficients of interest. This is the signature we are working in. The signature is slightly different here because, as you see, that the evaluation is mostly perturbative, and we are trying to use geometric methods. So, I mean, being Christian. So what recent investigations? So a lot of people, including authors here, that they have shown that these coefficients, this parity odd coefficients, are determined by the anomalies in the field. Now, let us just recall the anomalies, which we also focused here. So this is the current conservation law, okay, charge current conservation law, and here's an anomaly, okay, for that. And if you recall, this is stressed for the fermion, for a single chiral fermion, this coefficient works out to be squared by 4 pi squared. And there's a stressed anomaly, this conservation law of the stress tensor, and Cg here for the single chiral fermion is this known to be this number. Now, just again to put these numbers, sort of a little bit more for people who know conformal field theory, these coefficients are related in a conformal field theory if the theory is conformal, and this is for the free fermion. If the theory is conformal, these coefficients are related to the left and the right levels of this U1 current algebra. While Cg, this is much more familiar maybe, is basically the difference of the right and left central charges of the theory. So this is just to set, the fact that these coefficients are familiar. Some people might know this coefficient, some people might know this. So this is what the investigations have revealed. With the microscopic coefficients, the zeta 2. Recall, zeta 2 was the one which appeared in the U1 current. Lambda 2 was the one which appeared in the stress tensor. So zeta 2 is related to the gauge anomaly by this precise manner. Okay. And this relation can be established by this Euclidean partition function, which was developed by Shiraz and others. Lots of people here, students, and this can be established by that method, which relies basically on symmetries. And one more aspect which I'll emphasize soon. In this, using this approach, the second coefficient can be constrained in this manner. Okay. So there's a temperature squared dependent, and there's also a chemical potential. Mu is chemical potential dependent. Now the C tilde, this is of course again the coefficient of the anomaly. The pink ones are the coefficients which you see in the anomaly equation. The pink ones are the coefficients which you have seen in the anomaly conservation law, the macroscopic anomaly equation, while the green are the ones which you saw in the macroscopic constitutive relations.
Sorry, sure.
Yes,
with vacuum a little later.
Yeah.
Can you just show the constitutive
Okay.
ones? I'm really sorry.
Yeah. So that's here it is. So So this is 1 plus 1, so we are in the simplest possible case in which the anomalies, those parity odd coefficients occur at the 0th order derivative. So here it is. And you see there is this parity odd term, epsilon. Here is the parity odd term. It occurs at the 0th order.
Striking.
This is the most striking, and in fact,
for the order.
Yeah, in fact, I will say the consequence of that soon.
So just 0th order.
Zeroth order.
Fluid mechanics has.
Yeah, in fact, it affects hydrodynamic modes because it affects the 0th order. So that sort of we'll see soon.
And just out of curiosity, so does it now when you go? I know in 3 plus 1, it comes at second order.
Second order.
But what if you were in 2 plus 1? Is it at first order?
2 plus 1 parity odd.
Oh, you don't know parity. Sorry.
There is parity odd kind of terms, but
I mean,
whether they are microscopic anomaly.
Okay, sorry.
And then 3 plus 1, the lowest, it comes first.
First order. First order. Because you divide by one momentum. And 6 plus 1 it goes higher.
It comes at first order.
Same order of discussion.
Same order of discussion. Okay, sorry. Yes, I see. Thank you.
So that's the coefficient. So the green, so for instance, so this is determined by the microscopic anomaly. And here, so you can parameterize it in this manner, but here this coefficient is still not related to any of the anomalies. But, and it's not possible to relate it using this method of equilibrium partition function because it relies on the derivative expansion. Okay, and in fact, the gravitational anomaly coefficient Cs occurs at the second derivative in the conservation law. You can see that, for instance, backwards here. Okay. The R has 2 derivatives, so it occurs at the second order, while this occurs at the leading order. Okay, so there's a jump in the derivative expansion, and this method relies on the derivative expansion, and it's sort of not very easy to fix this coefficient, the relationship between the C tilde 2D and the gravitational anomaly. And in fact, the relation has been found, of course. The relation is this. C tilde 2D is minus 8 pi squared, the gravitational anomaly coefficient. And the method which was developed to find this is called the consistency of the Euclidean vacuum by Euclidean and collaborators. So this is the method. Let me just recall also the method, and just for the audience, though we won't do this way, just to recall the history. So how do they do this? How do you establish such a relationship? So you consider the Euclidean theory on the Euclidean cone. So here it is. So 2 dimensions. You go to the Euclidean space and consider the theory on the Euclidean cone. And here it is. So you see that delta equals 0. It's like a cylinder. dr squared r squared d phi squared here. Okay. And if you put delta equals 1, in fact you can do some change of variables and make it like dr squared plus r squared d phi squared. It becomes a plane. So you're considering the theory on the cone, and you have this metric which interpolates between cylinder, which is the thermal state, and the plane. And what you do is, it's sort of an adaptation of the equilibrium partition function method, as far as I can see. So you write down the equilibrium partition function to second order in derivative expansion, and let there be 2 parts to it. Okay? So I'm just schematically telling the method which discovered by Logan and collaborators. So let the gauge and anomaly diffeomorphism invariant part be W. Okay? It also contains parity odd terms, okay? And that has the information of C tilde 2D. Okay? So this is the macroscopic part. Then, of course, you have to add to this something which breaks the, which guarantees that the equation, the anomalous conservation law is satisfied, WA. So you have to add to this WA, and this contains the information of CG. And then consider the full partition function, and it evaluates the 1-point function of the stress tensor in the conical background. So this partition function is considered on the curved space, and you evaluate the 1-point function of the stress tensor in this conical background, which interpolates between the cone and the flat space. And this is what I think allows you to relate orders in derivative. But of course, there is this thing about the cone. But okay, we'll see that effect soon. It relates different orders and derivatives. Okay, and then you know that on flat space, so you will get you'll get a one-point function, which is a function of CG, which is anomalous coefficient, C tilde 2D, which is occurring in the transport coefficient, and delta, which is the conical defect, and you demand that the stress tensor vanishes in the flat space by translation equation, and that is delta equals 1, okay, when it's R2, and that gives you this relation. Okay, it relates the gravitational anomaly and C tilde.
Sorry,
yeah.
Might have said this.
Yeah.
What is WA again?
WA is the anomalous, the one which is sort of, sorry, I'm not able to. Yeah, so
This WA.
WA is the partition function which results in like the anomalous conservation law, which is anomalous,
Okay.
And that has two derivatives. Derivative is the second order.
How can you show that zeroth order term again? You have to make it out.
I'll write it maybe.
Yeah, and epsilon. I'm sorry, just once.
Epsilon. I mean, symmetries.
Symmetries.
Yeah,
Just as simple as that.
Yeah, it's quite simple actually. And it's Jamie.
Sorry. Yes, epsilon is.
Yeah.
Thank you.
You knew the first.
Oh, yeah.
Yeah.
You.
No, that's fine. That's fine. But that times.
Yeah. Plus. So what's our aim here? So this is sort of the background given. The aim is to explore this relationship between the transport and anomalies, and in particular the gravitational anomaly, because that seems to be the thing which is sort of very a little non-trivial, using perturbative methods, okay, so which I will outline soon. So what we do is we consider free chiral theories, like free fermions, free chiral fermions, free chiral, so you see the theories, and evaluate Kubo formulas for these transport coefficients. Okay, using finite temperature field theory, and let me just summarize the sort of rough results which we'll obtain. And so we do it for various cases. Of course, chiral fermions in 2, 4, and 6 dimensions, and cell-dual bosons in 2. Of course, chiral fermions and chiral cell-dual bosons are equivalent theory, and you see that explicitly. Relation. And we evaluate these coefficients explicitly and try to see whether how it's related to the anomaly directly. The relation between the gravitational anomaly and the transport predicted by this consistency argument agrees with the perturbative calculation for these chiral fermions and cell-dual bosons. Yes?
Is the dual fluid formed by these chiral fermions?
Huh?
Is the dual fluid two-dimensional?
Yeah, this is a free theory. So you don't have. You have to have. If you want a holographic dual, you need to be a strongly coupled theory. But So the question is why at all we should trust perturbative analysis. So of course there are arguments later on, but I might tell you a little later about it. But the rough thing, let me just say it roughly. This is an anomalous. This is controlled by the anomaly, and usually you expect it to be one loop exact. So you can just do perturbative analysis at one loop and trust it. Of course, to prove it perturbatively and all, it's a little hard, and I will tell you maybe what has been done towards the end of the talk.
So, Justin, what perturbation theory for a free?
So so it's basically like I will come to it. It's basically JJ, for instance, 2-point function of JJ, and just big contractions.
Okay.
Just big contractions. So I will come to it. Maybe the diagrams will come soon.
And related question. So, how is the transport in free theory?
So it's free theory at finite temperature and chemical potential.
Yeah, but it's still free, right? No interactions.
So these are non-dissipative transport coefficients.
Yeah.
These are the ones which are like the ones which are control. We can set frequency to 0 and value. So So, but what we will see is that this higher spin fermions, like of course, you would think, okay, hydrodynamics is chiral gravitons, but it's a conceptual question, so you should allow me to ask it. So, higher spin fermions like chiral gravitinos contribute to the gravitational anomaly, okay, 2 and 6, in 2 and 6. But the relations like this, which, for, like you take the gravitino, anomaly coefficients of the gravitino and check whether they contribute exactly with this formula, is not true. It's not true for these chiral gravitinos. And in fact, from the perturbative calculations, we see chiral gravitinos effectively contribute to the equivalent of d minus 1 chiral fermions to transfer. So it doesn't satisfy this above relation. And what the perturbative calculation will teach us is that how exactly this relation breaks down, at least in perturbation theory, where is the possible.
I'm a bit confused. I thought this argument of Loga and so on was a general argument.
Yeah, it's a general argument. From that point of view, it's other than the fact that somehow the chiral gravitinos at the cone they behave differently. That's what people see. So it seems to break down for the chiral gravitinos. That the argument seems very general. Yeah. Of course, they use the calculation of partial function around cones and so on. Which,
Did they anticipate it would break down?
Yes. Yeah. So Loga, I think, in a subsequent paper anticipated that it was breaking down using. I think he has another way of evaluating this using helicity trace, and it is where they anticipated. And here it's a different direct calculation.
In gravitino, you just any higher spin, I imagine.
So I think the
this
self-dual bosons might go through. Self-dual bosons in 6 dimensions and so on. I mean, they have this
spin zero.
Yeah. Which is
with some constraint.
With some constraint. That goes through. But this higher spin fermions, meaning anything which has this mu and fermion, those kind of stuff. We'll see why it's happening, and then it'll be clear how it's happening. Okay, so then the second thing, which if I get time, is that as you've seen, that it occurs at the 0th order. So it's really starting in 1 plus 1 dimension. It occurs at the 0th order. So therefore, they must affect hydrodynamic modes at the leading order. Okay. And in fact, in 1 plus 1 dimension, there are 3 hydrodynamic modes, 2 sound modes. One is moving left and one is moving right, and charge diffusion mode. And the charge diffusion mode actually, due to the presence of this anomaly, it acquires a speed. And for this free Weyl gas, which we can actually explicitly calculate very simply, the speed is actually half the speed of light. So there's a consequence of these things also.
So in the absence of this term, the dispersion relation would be at leading order omega equals 0.
Omega equals 0, yeah. Or, if you put the dissipative term, it will be minus I d k squared. So let me again, so we will, I don't know how much time I will have, but let me at least try to finish the story in 2 dimensions. Okay, again, let's recall the constitution.
And does it change the speed of sound as well?
Speed of sound is not changed, yeah. But like if you keep the dissipative term, it will feed in there. It will feed in there. So consider the constitutive relations again. So they occur at 0th order. One simple way to obtain this thing is, of course, you go to the rest frame of the of this fluid. So it will be like 0, 1. I mean, rest frame like you not use of this kind, 1, 0. You go to the rest frame and just evaluate the expectation value of the stress tensor in that particular frame. Then you can actually pick out this, because like 0x will pick out only this. 0x will pick out this.
So are we in a formal field theory or arbitrary field?
Arbitrary field. I mean, actually, finally, it will be only free chiral, the way I'll calculate. I mean, I'll calculate only free chiral fermions. Okay, so this, but this is a way of computing zeta 2 and lambda 2. But we won't. So this seems easy, but we won't do this. We will do a little bit more different one, so that it captures the features of the higher dimensions generically. So to indicate generic features of higher dimensions, we evaluate the same transport coefficient using these formulas. So there is equivalently another formula for this. So zeta 2 is basically the 2-point function of the current with the stress tensor. It's basically, I mean, you just have to look at that constitutive relation and do some small fluctuation analysis and read out the response, from a 2-point function. That also is possible here. Basically, this has a raising and lowering g, and and this also has raising and lowering g. And so, if you differentiate this with the metric, this also it picks up zeta 2. So I want to do it this way because it captures the generic features of this, the calculation in higher dimensions. So this is the 2-point function, and we need to evaluate these 2-point functions in perturbation theory. So what is the strategy to evaluate these 2-point functions? So we'll evaluate the correlators in the Euclidean theory at finite temperature and finite chemical potential. Then analytically continue to real-time Minkowski correlator. So here's the standard prescription for doing that. And when you do it in the Euclidean theory, of course these are Matsubara frequencies, and the external frequencies are integer moded, and the internal ones, when the fermions are running in the loop, will be half integer moded. And then we'll continue back to Minkowski. And when you do all that, you have to be a little bit careful. I mean, here it is tau, here it is t, and because of that, you have to take the tensor transformation properly also. So you've got to do it carefully, but it can be done. Okay. And you have to continue it back. So that's the sort of basic strategy to evaluate these correlators. And this is the theory we do. Right? So chiral fermions, 2 dimensions. This is a simple action. And this is the gamma matrices and so on. And here is the covariant derivative. Here's the covariant derivative. And in fact, in 2 dimensions, there is no spin connection. If you think of the index structures carefully enough, there is no spin connection in 1 plus 1 dimension. And here is the background gauge field. Here is the gauge field. And this is the standard action, actually. And correlators are evaluated. Hello?
Can you hear? I can hear.
Yeah, yes.
We can hear, but we cannot see the slide.
Oh.
Yeah.
Yeah, we can see the slide.
Yeah. So the correlators, as I said, is evaluated at finite temperature and finite chemical potential. So we consider the theory on S1 times R with antiperiodic boundary conditions for the fermions. And to have a finite chemical potential, we turn on a background gauge field in the time direction. Here it is. We turn on the background gauge field in the time direction. And the Euclidean propagator is simple enough, actually. It's given by this expression. Okay. It's basically, 1 by gamma slash t, or p slash, sorry. But with appropriate modings and the chemical potential fed in, this is the chemical potential we use. There is this chemical potential for the U1 and for a chiral kind of chemical potential. And as I said, it's a chiral theory. The P minus in the action, which projects out to the chiral part. And this is the propagator. It's a 2x2 matrix. These are just structural things to remember. And so here, this transport coefficient is basically a 2-point function, which is given by this expression, where z is e to the power of s, e, the condition function, g psi bar, with the background and everything. Okay. And if you go through the definition. We go through the definition and just evaluate this. You will get, of course, the disconnected part. This is the disconnected part. And here this connected part, here it contains both disconnected and connected, and we cancel that. So it's a connected part of the correlator we are looking at. But there is also this term, this green term, which is sort of important, and it's an important feature in higher dimensions. That's one of the reasons I showed this. Where the derivative hits the s twice. Derivative hits the s twice. It's all roughly like a contact term. So this term is present in higher dimensions also. It's important, otherwise you'll get a wrong number when you do the calculation. So there are two contributions. One is from here. So as you see, this is roughly the current itself. Del S by del A is the current. And del S by del G is basically the stress tensor. So this is the JT2, the usual contraction. And this is the term that the two things are together. Yeah.
Can I just ask you?
Yeah.
Suppose I was to, this is very nice, but if I was just to try and understand it in a dumb way, is it the same as, so the expression for the stress energy tensor as an operator remains what it is normally, psi, dz, psi, or whatever.
Right.
Similarly for J, and we then evaluate it in its state that the chiral mode is thermally excited. Is that
but that's correct. But you have to so stress tensor. Let's look at stress tensor. The stress tensor, you will have some structure like this, no? Some structure like this. But
I mean, if I've just got a left moving fermion or something, and I'm in the end interested in flat space 2.5.
But then we are looking at T mu J mu curvature. So then you have to differentiate this with respect to the A.
If you like, or just compute a 2-point correlator in a thermal state. Should I just do that?
You can do that, but I think you will miss this term, for instance. Because see, you have to see this in curved space, and then when the derivative again hits it, it will hit something here. Like suppose you see this in flat space. If you see this, if stress tensor is seen in flat space, so then if there is no background here at all, then it is del A mu by 0, right? So there are terms like this, del S by del A. There is a current in the background, in the curved background, and then therefore there is a contribution that del S del by del G.
So conceptually, the left-hand side is not just the standard stress. It's a standard current in a thermal state.
Right. This is not flat space Euclidean cosmeter. It's not that, because this is the definition of the Hugo formula. I mean, this is the definition. You just take it in the curved space and you differentiate.
So you have to be careful.
You have to be careful. I think you'll miss that. In higher dimensions, it's very important because I think you'll see it later. And that's why I wanted to see it and show it in one. So there are, this took us quite some time to figure out actually.
Can you go back to the slides?
We can see this.
Sorry.
Thank you.
Okay. It took us quite some time, and we were getting just factors of 2 off, and we thought we were making some other mistake, but it was actually quite a conceptual miss because it contributes equally. In this formula, it contributes exactly equally. These 2 terms contribute exactly equally. There is this. These are the 2 possible diagrams, and here it is. So as I said, this has 2 contributions. This is just, as we were discussing, this is just the flat space correlation functions, where this is all flat space. And the B is of this kind, basically. Psi dagger, psi, this B is like this. There is one gamma matrix inside. And the propagator provides another gamma matrix, and so it can saturate the gamma 5. So there is this kind of B, this time. And if you evaluate the diagrams, you can see A is A is basically you have fermion, fermion, and correlation like that, and with some derivative because there's a stress tensor, and that gives this extra momentum. These are the 2 kinds of propagator structures, and you can do the internal integrations. One of them is actually sum over Matsubara frequencies, and you can do that using the usual contour integral trick and so on. What happens, what is interesting after all that thing is that it actually just reduces to a moment of the Fermi-Dirac distribution. Okay. So A is just this, like a moment of this F is the Fermi-Dirac distribution, and A is just the moment of the Fermi-Dirac distribution, and B is also finally a moment of the Fermi-Dirac. In fact, they contribute equally in the zero momentum limit. Both are moments of Fermi-Dirac distribution. This is a good structure to remember actually, because this is what repeats on and on. And these integrals, these moments of the Fermi-Dirac distributions are known. And putting together and taking the zero momentum limit and the zero frequency limit, you get this particular answer. So you see the chemical potential, the charge E squared by 2 pi, and so on. So it's after doing this calculation, it's quite a simple answer. Let me just summarize. I've been trying to capture the essential features. So both A and B, the contact term contributes, and this is a feature as I mentioned in higher dimension. And in higher dimensions, these things come from the spin connection actually. And one needs to carefully evaluate all these terms. And the final result, so this result finally is an important feature to remember, that it's moment of the Fermi-Dirac distribution.
So even though you've got a contact term in position space,
yeah. In momentum space,
it just contributes.
Yeah, it just contributes. Yeah, that's a simple integral. It just contributes.
So maybe later, but you know this. Yeah. Suppose I added another contact term to this.
Another contact term.
Yeah. Is some contact terms should not contribute.
Yeah.
It should be only some contact terms of it. You have a similar thing in your cosmology, right?
Yeah.
That's right.
In momentum space again.
Yeah. You just show the contact term again.
Oh, sorry. Yeah, here it is. This one. So here you just have to with contract psi with that. So when you with contract psi, there is one gamma matrix. And there's already a gamma matrix here, and P has two gamma 5 basically. So that's how it saturates. So you'll have to look at contact terms which saturate the gamma 5, this whatever analog of the gamma 5.
It's obvious that this is a local term.
Yeah. We actually got it from the action. We expanded the Weyl out to the second order. That also had to be done quite carefully, and there were several mistakes initially. But yeah, you'll have to expand the Weyl to the next order and calculate.
Sorry, but sometimes contact terms are can be done away with a suitable field redefinition or something.
And in this case, the field is just your source, right?
Yeah.
And maybe the agent and I was thinking exactly the same thing. But suppose I had just a scalar operator, and you say W of j is e to the power I j o. Then to that generating function, if you just add some local polynomial expression in j, that's supposed to be sort of unphysical, right?
Yeah.
But those contact terms can't be redefined away by this. Are supposed to be physical. That's roughly my understanding of these contact terms. And somehow the kind that you're talking about is a physical.
Physical, yeah. I think it is because of course there is the other way of many ways of checking this thing out. That's what I see. Yeah, this issue of contact terms was not settled in the first evaluation by Landsteiner in 4 dimensions actually. So of course the answers are just multiplicatively off. So you can and also a polygraphic check was there, and so you can easily get it. So fine. So now that we have this thing, we have the transport coefficient. We can compare it with the anomaly. Okay. This is for the chiral fermion, and then you can just see that this is the formula which was this is the formula, of course, derived by also from the Euclidean partition function. For the gravitational one, lambda 2. Here are the now I've just mentioned roughly the diagrams. So there are these kinds of diagrams. This is the usual flat space one, and there is some particular term like this. And again, here, finally, when you do all the integrals, it turns out to be the first moment of this Fermi-Dirac distribution. And that also, in terms of Bernoulli polynomial, there's a nice compact answer, and it turns out to be this. And you see the structure of the temperature squared coming out. And you can again compare it with this parameterization of the anomaly. And of course, this lands up right into this is a counter check, second check for the gauge anomaly that it works out. And here there is this coefficient C tilde 2D. And from the explicit calculation, you can compare what you got for this coefficient, and you see that it obeys this relation. Okay. And this is for this chiral fermion. And for chiral boson, we have repeated the calculation for the chiral boson, which is of course a spin 0 object with a constraint. Here is this T mu and J mu. And here also you have to be careful about the contactant. But here the modes are quantized in integer modes. So it's actually Bose-Einstein distribution though. But if you evaluate these point functions, and of course you have to relate the boson charge to the free fermion charge by this formula, and you of course wind up with the same answer. Okay, so it was like a sort of check also for us. Now here is the thing: this gravitino-like system. So of course there are no gravitinos in 1 plus 1 dimension. I mean the number of constraints for the gravitino is too much. But I'm going to mimic one. In 6D is where it comes out, but I'm going to mimic one by this particular Lagrangian. It's almost like a gravitino. Actually, it's a gauge-fixed version of the gravitino Lagrangian. This is just to mimic and see show the features in 1 plus 1 dimension. So here is the usual. It's almost like the Dirac Lagrangian, but you see that this has index, this gravitino index, and that's contracted. And because of that, the only difference between the usual fermion, of course, there is this index, there is multiplicity, but there is also this Christoffel symbol in this case. There is a Christoffel symbol, and this is, of course, I mean, as I said, there is no gravitinos in 1 plus 1 dimension, but it's just sort of toy model to mimic features. And we have to, in a regular gravitino-like system in higher dimensions, you have to subtract out a ghost, and this is equivalent to like 1 fermion basically. But we'll come to that later. And as I said, so because of that extra Christoffel symbol, there's an additional contribution to the stress tensor. Now this is the usual stress tensor. Dagger, with the index taken into account, this is the usual stress tensor. But there is an extra contribution to the stress tensor, which has roughly like a derivative sitting outside. Okay. So there is this extra contribution to the stress tensor. Okay. When you just linearize the Christoffel symbol and just compute it, you will get this extra term. Now let's try to make some sense about this extra term a little bit, and let us go to familiar set of coordinates to make sense of this extra term. Okay, so we go to this holomorphic coordinates, minus I tau plus x, and then rewrite the stress tensor again. There's only this holomorphic zz part of the stress tensor when you write it in these coordinates. And again, this is the usual term. Okay. And here is this term from the Christoffel connection. So there is this, it's like an improvement kind of term.
It's like a BC term.
Yeah, it's like a BC term. Yeah. So there is an improvement kind of term del of that kind of stuff.
So you're not working at lambda equals half anymore.
No. Yeah, it's just this is what you get just from that model system.
And then I is to be taken seriously?
Yeah, there is an I.
In the usual BC system, there's no I.
Yeah,
right?
but I guess maybe this is Euclidean and I don't know epsilon mu nu. It turns out this is real actually. It's real. If you take the dagger and there is a sign from here and so on, it turns out.
What's the central charge?
Yeah, so that's what I'm going to evaluate. I'm going to evaluate the central charge. Yeah, so that's what. It's not physical. That's the reason. It's not physical. It's negative. It's not physical. The system is a toy model. It's not it's a mimicking toy model. So evaluate the central charge, and in fact, this gives you the gravitational anomaly because there is no right movers, and this is the gravitation. That's one of the reasons to evaluate it even. So this too is coming from the usual term, usual part of the stress tensor, and this minus 24 is what comes from that.
Why is the usual thing 2? What 1?
Well, this is actually complex fermion. I'm taking complex fermion.
But mu has 2 values.
Mu has 2 values.
So it's 4.
Yeah. So this minus 24 comes from that actually.
From
this thing. Yeah. So 2 relates to the first term and minus 24 relates to the derivative.
Sorry. So minus 24. If I just take half of this, so for one of them, that's 1 and minus 12.
Right.
And is minus 12 what you get for the BC system at some nice value lambda?
Yeah, I didn't check. So
okay, that's right.
Yeah. there will be one lambda.
There will be one lambda. I'm just wondering whether it's imaginary or okay. Yeah. So some
lambda. Yeah. So of course there is this ghost system which I didn't bother with. This is just the system. We have to subtract out 1. And if that system is also there, there will be minus 23. And in fact, Logarithm and all, I think in his later paper, he has some Gravitino-like system, and which he doesn't do the calculation this way. He just extrapolates anomaly polynomials, to do dimensions, and he gets these expressions. So this is the same answer he gets. So this is the formula. So this contributes to the gravitational anomaly, and this is the relation between the central charge and the gravitational anomaly. So we know CG now for the system, and you can see that crucially that improvement term did contribute to the central charge. Now let's see what happens when you do the transport calculation for that particular term. So when you do the transport for lambda 2, okay, so TT we have to calculate, and this A is that first term, the usual stress tensor, and B, and there is no cross term because of that epsilon sitting in there. There is no cross term actually, and they come differently. And when you evaluate the second term, okay, there is an overall P squared, so the overall momentum squared in this when you evaluate that particular term. This is the answer for that evaluation, and there is a P squared, and of course it vanishes in the zero momentum. So this contribution just totally drops in this transport calculation. Okay. So for the purpose of transport, the system just behaves like 2 copies of Fermions. And in the zero momentum limit, it just drops out.
It's 2 copies, not 4 copies, or whatever.
Yes, 2 because mu. Yeah, I'm just sort of putting psi as 1 and then mu. 2 complex fermions. 2 complex fermions. Yeah, so this is the feature, and this is the reason. And in fact, we also, of course, studied the contact terms also arising from the crystal symbol, and all of them have this particular property.
But in non-zero momentum, the response.
There is possibility, and in fact, we didn't study how it actually, it might feature. We didn't study that actually. Yeah. That's worth looking actually how it those terms contribute. So the perturbative calculation is identical to these 2 chiral fermions, and there is, in a Gravitino-like system, it comes with a ghost, so we subtract the ghost, and basically it is equal to 1 chiral fermion then complex, and we have this, but this is certainly not that 23. There is some 23 hanging around, and you cannot have this particular relations. Okay, so this relation is violated actually, and the violation you can clearly see is just from that Christopher connection, which contributes to the central charge but doesn't contribute to the anomaly. So the general lesson is that terms arising from the linearization of the Christopher connection do not contribute to transport at zero momentum, and so it basically the Gravitino behaves like d chiral fermions, and we have to subtract out, and it's equal to d minus 1. This feature, of course, we carefully checked in the 6-dimensional case. In 4 dimensions, I will come to that later. 4 dimensions, actually, it doesn't contribute, gravitations don't contribute to pure gravitational anomalies, and therefore that question doesn't arise actually there. So 4 dimensions. So now I'll just quickly summarize the results. There are 3 transport coefficients. These are the ones. You see, basically, it's various power, the JJ, JT, and the TT. So there are 3 of these things. They occur at, as I said, first, as we were discussing, first derivative, you have to divide by momentum here. And these are excitations in the Z direction, and all the others are in orthogonal directions. See? So there is, so we consider the theory of free chiral fermions, follow the same procedure. And the additional ingredients which I couldn't show you in 2 dimensions is that there is a spin connection which contributes to contact terms. And the one-loop integrals now are not just simple dp integrals. They contain angular integrations also because it's in high dimension. And we developed a simple prescription actually for handling the angular integrations. Okay. which for 4 dimension we checked both ways actually. So we can actually take the zero momentum limit first and then perform the angular integration. It's quite easy to perform there. It's quite trivial actually. It drops out. And then do the angular integration. This prescription is very useful, especially when you go to higher 6 dimensions. It's so very useful for us. And once you do that, actually you can see using this prescription that the method directly relates the loop integrals to this moments of Fermi interactive distribution. So this is the technical simplifications which we found. And here is one particular contribution. For the T basically, there is the usual one, and there is this kind of term which we have located. And here are the results again. So you see there is this gauge anomaly term. Here's the gravitational mixed. Here it's called the mixed anomaly coming in. And these are its terms from 3 transport coefficient. And you can actually, you can actually compare it to the anomaly coefficients. So here is the usual gauge anomaly term, and here is the mixed anomaly, Ca and Cm. And these are the coefficients for a chiral single Weyl fermion. You can actually compare. So because we have calculated it directly, you can actually compare it, and you find these relations that the first here is this. You can recast the first transport coefficient in this manner. The second one with temperature also is there, and in fact here again the relationship is true. This relationship. And even from the direct and forward. So there is a counter check for Ca here, and there's a counter check because of the 3 transport coefficient and only 2 parameters. And here also there is a check for using the second. So these satisfied as expected, and they are chiral fermions, and the argument meant. And here, one thing which I want to point out is that gravitinos cannot be charged in flat space without breaking the symmetry. So therefore, they don't contribute to any of this charged current. It's important to realize that, and they have no mixed anomaly actually. They contribute to no mixed anomaly. So in 4 dimensions, there is no question of asking about the gravitinos actually, because they don't contribute to charge transport. Now in 6D, same method, and we use that prescription which we developed for handling the angular integrations. There are 4 transport coefficients again, and in fact this is a 3-point function. Now it's a 3-point function, j, 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 and j, j, g, j, t, g, and so on. 3-point functions, and 2 momentas, 2 different momentas in 2 different directions, and these are all different directions. A, x, z, y, and e are different directions. So you evaluate them, and it gets involved actually. There's a sort of an exchange diagram for the first kind of term. So this is basically like stress tensor, stress tensor, stress tensor kind of calculation. These are like the contact terms. And here's the answer for various species. So these are the fermions, and the gravitino, of course, contributes only to the only all stress tensors. There have to be only stress tensors for gravitino. So and here you see the relation. So if you look at just the stress tensor contribution, without any chemical potential, this is 5 times this answer. So this answer is 5 times this answer. This is what we said. The gravitino has to be 5 times that of the contribution of the chiral fermion. And that we see that explicitly also. I haven't shown all the details, but if you do the calculation, you can see the reciprocal connection term dropping out explicitly when you take the zero momentum limit, and it is just as though it behaves like fermions. Again, this is what I was saying, that the contribution of gravitinos is equal to 5 times that of the chiral fermions, so this is the thing. So again, we can compare it against the anomaly coefficients, and here also there's an interesting feature. So there are these anomaly coefficients. So this is the gauge; these are mixed, and this is like 0.12 integral P2 squared or so, and this is like P4, I think. And there are 1, 2, 3, 4 anomaly coefficients actually, and parallel fermions, all of these are these values. But it's only 3 of them which contribute to transport. And this feature was also seen by Euclidean in his method. So in fact, it's only C alpha, C beta, and C gamma which contributes to transport. C delta doesn't. Okay, we have done explicit calculation and we see this, but I don't see some deep reason why it is only this doesn't contribute.
Which one doesn't contribute?
This one, C delta. Yeah. Why this doesn't contribute. But in our explicit calculation, yeah, we see that. So this is just explicit. The green, as I said in the whole thing, is the macroscopic. These are the microscopic coefficient, and everything can be cast in this manner. And so, of course, this the mixed one is related to my 8 pi squared, and then there is this C gamma, the new gravitational anomaly, C gamma, and that is 8 pi squared the whole square. I think in our normalization. I wanted to check with Loganarian's one, but somehow, I think he didn't have the patience and I didn't have the patience to check the correct normalization. But I think it is correct. 8 pi squared, the whole square is what comes here. So this, and as I said, the C delta does not contribute. And here again, the gravitinos is 5 times that of the parallel fermion, and it doesn't obey the consistency of the Euclidean vacuum. And in fact, C gamma for graviton is some awful numbers, 275 and so on, and it doesn't obey that simple relation. So let me just summarize, because it has, a lot of people are actively doing this, and I just want to place this thing a little bit in context. There were partial results from direct perturbative calculations before, actually, especially in 4 dimensions. By Landsteiner's group, okay? But I think this contact terms was not taken into account very carefully. But since holographic answers were known somehow at the scale, so our computation is complete with also the detailed transport for the treatment of the gravitational anomaly. And in D is equal to 6, it's sort of the test of this replacement rule of Loganarian. And so let me just conclude with this interesting feature which we see in 2D Weyl gas. As we saw it before, starkly, this transport parity order occurs at leading order, and it must affect the leading dispersion relation. Here it is again. So here I've written it in Landau field, basically to make a change of velocities. So I've included the dissipative term also, but it's not important for the discussion actually. So this is like bulk viscosity which I included. But I have moved all the lambda 2 and zeta 2 all to the current, because I made it, the reason is that we have done these hydrodynamic modes in Landau frame first. So I moved it here, and zeta v is related to the zeta 2 and lambda 2 in this manner. And there's a frame change actually.
And Landau frame is what? U mu T mu
is 0. Is 0. U mu T mu contraction is 0.
It's from the correction.
From the correction. From the correction.
It's the 0th order.
Yeah, 0th order. Yeah.
It's the energy.
Yeah. So you shift velocities and you can move it to this one actually. This is the thing. And so we consider small fluctuations from the rest frame for charge and energy. Okay. And you get some linearized equations. So we had studied this earlier actually, so it was easy for us to do it. So this is the sort of it's sort of a linearized, and you see all these are linear, and it's a 2 cross 2 matrix basically equals 0. So for non-trivial solutions, the determinant of that has to be 0, and you can solve for the dispersion relation by assuming this form. Okay. And substituting it, so the leading order, you get a constraint for B actually. The substituted and demand determinant is 0. And for the leading order with K, you get a condition of this kind. And in fact, it's a cubic equation of this kind. And you see this term which is coming here, the last constant term, is basically proportional to the anomalous one. So if this was not there, you just get 3 roots, and one of them is 0. One of them is 0.
That would have been the
Yeah,
charge diffusion.
charge diffusion. That's the charge diffusion. So if that is there, of course, it develops a velocity. Yeah, this is what I was saying. When this is 0, okay, this is the sound mode. You can see this, without the charge density, you can see it's a ratio of pressure by energy, root, which is the sound speed. So that's the sound mode, and then there is the other one is 0. But if you turn this on, okay, so we do it, it's a very nice equation for the ideal Weyl gas. So otherwise, okay, you can get some expression, but it's not. So for the Weyl gas, the thermodynamics.
Weyl means just one fermion.
One fermion, yeah, one fermion at 3 fermions.
3 fermion.
Not special constant, just 3 fermions. So, and this is the energy density, and this is the charge density. And you can evaluate this, and everything organizes very nicely as rho by 2. I mean, it's quite actually. This whole thing organizes as a rho by 2. You just have to substitute everything. And B and A are the same, and so on. Things organize nicely. And there is some simplification in these derivatives also. And basically, the cubic equation is very simple. It's just this. And there are 3 roots, plus, minus. And of course, if the chirality is changed, it's plus half. So there are these 3 roots. So that's a small feature of 1 plus 1 dimension. And first roots found in the. So let me just conclude. So the direct method of evaluating parity or is perturbative, and we have, of course, as you've seen, we have observed these coefficients at 1 loop, and it will be interesting to prove a non-denominalizing theorem in perturbation theory. Of course, you expect it, but it's interesting to see this actually, of course, for d is equal to 4, there is evidence from holography actually that these coefficients are not very normalized. And it will be interesting to see explicitly perturbative arguments for that. And it's also worth, because of this fact about this conical defect and all that, it's worth checking it for the cellular tensor and d equals 6. This is quite a tedious calculation actually. But this student of mine has developed certain routines to do all the big contractions. So it's possible that we can do this calculation. And there must be a way of correcting. So this is sort of very open-ended, but there must be a way of correcting the predictions which are seen from this Euclidean consistency argument. And there must, because of this conical defect, maybe there is some sort of correction we can do, and so that the answers work out, and it might lead to this better behavior understanding as control. That's all I have to say. It's so nice.
Questions from ICDS?
Only 2 fellows there.
Yeah, I think 2 of them are my students, and I don't know what to ask. I can't speak.
Sorry, were there questions from ICTS?
No questions.
No questions. Okay. Do you have more questions?
I know this is a bit of an aside.
Cool out.
I know this is a bit of an aside from your own talk, but just to, I haven't studied this, in this Logarithmic conical defect or whatever method, so what I understood was you evaluate the partition function then in this metric which sort of interpolates between the cylinder
vacuum
and the Minkowski or Euclidean planes. And then, but basically you put the system on some manifold which is non-trivial enough that you can extract a stress energy tensor as a response to the metric which is then sensitive to these stuff. To the extent that there are subtleties because you are working with a conical geometry which has a curvature which is then concentrated in a sort of somewhere at the tip of the cone. Can you basically use that method but smooth out that singularity a little and evaluate the response?
Yeah, I understand. I didn't think of one.
Because that seems to be a powerful way otherwise.
Yeah. There should be a way actually. Because another thing is that, I mean, there are independent calculations by Furasev, who has done this, and he sees that, you know, if you take this kind of limit, direct limit, you know, of the conical, there is a problem. But if you smooth out, you can get better answers. And he's seen it for just partition functions of these gravitinos on holes. I mean, so there might be a way actually. So yeah, but it's sort of I haven't formulated enough to sort of, you know, pinpoint where exactly this is failing.
Other questions?
I can ask one more, but I should
Sure,
wait.
excellent.
Okay, the other one is more open-ended, so maybe, but I mean, as we all know, and you all talk about it, I mean, there are these beautiful connections between descent formulas for anomalies and so on. And in particular, what I wanted to ask you was, if you take a quantum Hall system in 2 plus 1D, then it has a sort of parity, it has a Chern-Simons-like description with its, and then on the boundary you get chiral edge modus, right? And now, aren't you telling us, and I think in some cases you just get one Weyl formula also, right? And what you're telling us is that there is an anomaly there which affects transport then for those edge states in the Hall system. And is this new?
Yeah, I don't know. That's what I looked around this, especially this manifestation of this hydrodynamic mode, because it looks very stark actually.
It's so stark. Hydrodynamics.
I looked around, but I couldn't find any. I mean, I searched for some time actually. I couldn't find anybody who was. I asked him, but I think there was no. I couldn't find this kind of system at least.
Actually, just to follow up on that. Suppose we're looking at a conformal system, like you're free to master this for now. Then in the absence, just on the plane, and in the absence of a background F, the equation for the charge current and stress tensor is just that of holomorphism. Is that right?
Conservation.
Let's say that again. You have a conformal field theory in the absence of any background fields.
So let's look at the current, for instance.
Yeah.
Is it right that J minus is a function only of sigma minus and J plus is a function only of sigma plus?
Yeah, because in the absence of the field, you
Yeah,
still have
then mu and J mu is 0.
So what I had thought was that there was no possibility of anything interesting for a conformal fluid in 1 plus 1 dimensions for this reason, that holomorphicity is the solution to the equations of motions. So if J minus is a function only of sigma minus, then everything automatically moves at the speed of light. Anything that's a function only of sigma minus is always moving at the speed of light. Similarly, if T minus minus is only a function of sigma minus, it just describes things moving at the speed of light, right? Whereas you seem to be finding more interesting dynamics, because you find something moving at half the speed of light.
Yeah, for this particular case, I mean,
so I want to understand how these were consistent.
Yeah, we thought, I mean, I'll tell you the way. Because, I mean, the one thing, let me show you those equations actually. Yeah, so these equations, you see, I mean, so let's see this relation. I mean, if you set mu is equal to 0 first and calculate it, okay, calculate these. This one, if you set mu is equal to 0 first and calculate this turns out to be 0. Mu is equal to 0 first and calculate. But you turn on mu and then do the calculation, and then the answer somehow is independent of mu. I mean, because you take the ratios and so on, it turns out to be independent of mu.
But just to understand, do you have a lump that is actually moving at half the speed of light?
Yeah, that.
Because the holomorphicity would seem to suggest that everything that moves at the speed of light. And the special thing about 1 plus 1 dimensions is that, for instance, if you do the counting, if you look at a stress tensor in 1 plus 1 dimensions, if it's conformal, if it's traceless, then there are 2 components to the stress tensor and 2 components to conservation. So you might have thought that you don't need to move to hydrodynamical variables in this case. You just directly solve for the stress tensor itself. Or T, yeah. normally hydrodynamics is a useful thing because there are fewer hydrodynamical variables than stress tensor components or than charge components. Here it looks like it's the same. And so there doesn't seem to be much gain in going to velocities. Just directly work in terms of the stress tensor and then we know the solution. It's just P minus minus.
J mu in the case, in the including whatever the additional term was, epsilon mu mu mu, right?
Yeah. Right.
That's epsilon, right?
That's epsilon, yeah.
And now, and then how does the current conservation
Yeah.
So this is now some Landau.
Yeah. So this is in the Landau frame. Yeah. It's not so nice here, but yeah. So this is how it comes, and del mu J mu. Yeah. That's how. So that implementation of del mu J mu equals 0 and del mu T mu equals 0 is this.
Is this?
Yeah.
Is this?
Yeah.
Implementation of del mu J mu is
I think
0 and del
it's
mu.
just free for me also.
I mean, initially it is not conformal, but final application of the formula is for a conformal system.
Yeah. I must be saying something wrong.
Yeah.
One thing that could go wrong is that could be sometimes it happens in conformal field theory that a current is conserved without being, J minus is a function only of sigma minus is one way of satisfying the conservation. Sometimes it might be more complicated. Okay, anyway, I'll ask you.
Yeah.
But if del mu J mu is not 0, if there is a background, then this counting doesn't work. It's not working.
But there is no background. In the end, we are applying it to no background. You can use whatever tricks you want. But in the end, we're looking at the motion of stuff in the absence of a background. In that case, del mu J mu is 0.
Yeah. So this is basically, if you remember, this is the modification of the equations which we derived a long time ago with this zeta, especially with the zeta.
Is this limit between fields singular? Because clearly
there is a problem with taking the limit mu first 0 and evaluating it and so on. Actually, yeah. There is discontinuity. Suppose you put mu is equal to 0 first, then evaluate, then there is nothing.
So let me ask you the following. In your mode, if you evaluate the current, does the current move at the speed of light or half the speed of light?
Oh, that we didn't. We just saw the dispersion relation.
It has to be half the speed of light. Anything moves at everything. It's very interesting. I don't understand it sometimes. Other questions? Okay. If not, thank Justin again.